They carved stone as if it were clay, lifted weights that modern cranes would struggle to move, and aligned monuments with precision that still embarrasses our most advanced instruments. Long before digital computers, steel machinery, or electric power, ancient civilizations across the world achieved engineering feats so vast, so precise, and so enduring that they continue to unsettle modern logic. These were not isolated accidents of genius. They were systematic, repeatable achievements embedded into entire cultures, passed down through generations, and executed on scales that challenge our assumptions about the limits of ancient knowledge. We tend to imagine the ancient world as technologically primitive, progressing slowly and blindly toward the enlightenment of modern science. Yet the evidence carved into mountains, etched into bedrock, and standing silently across deserts tells a different story. A story of lost techniques, forgotten sciences, and engineering traditions that seem to emerge fully formed, with no clear developmental trail leading up to them. Structures appear suddenly in the archaeological record, already perfected, already precise, already monumental. Consider the stones themselves. Many ancient structures are built from blocks weighing tens, sometimes hundreds, of tons. They are not roughly shaped. They are cut with flatness and symmetry measurable to fractions of a millimeter. Their joints are so tight that even today, razor blades cannot slide between them. These stones were not simply stacked. They were interlocked, shaped to distribute seismic forces, designed to survive earthquakes that have destroyed entire modern cities. In the highlands of Peru, massive walls composed of polygonal stones fit together like three-dimensional puzzles. Each stone has multiple angles, each face smoothed and shaped to lock perfectly with its neighbors. There is no mortar, no binding agent. Gravity and geometry alone hold the walls together. Earthquakes have shaken the region for centuries, yet these ancient walls remain standing while modern concrete structures crumble around them. The logic behind their construction suggests a deep understanding of structural dynamics, stress distribution, and seismic resilience, knowledge that modern engineers had to rediscover through trial, error, and failure. The question is unavoidable. How were these stones shaped? The hardest rocks used in these constructions, such as granite and diorite, rank near the top of the Mohs hardness scale. Modern methods require diamond-tipped saws, high-speed drills, and industrial abrasives. Ancient explanations often rely on simple tools, copper chisels, stone hammers, wooden wedges. Yet experimental archaeology repeatedly fails to replicate the precision and efficiency seen in ancient stonework using these tools alone, especially at the scales involved. In Egypt, granite blocks quarried from Aswan were transported over 800 kilometers to Giza. Some of these blocks weigh over 70 tons. They were cut with straight lines, smooth surfaces, and right angles that remain accurate to this day. Drill holes in these stones show spiral grooves consistent with advanced rotary drilling, implying speeds and pressures difficult to reconcile with hand-powered tools. Even more puzzling, some cuts appear to slice through quartz crystals cleanly, a feat that strains explanations based on copper implements and sand abrasives. Transportation poses an even greater mystery. Moving stones of such immense mass requires not only strength, but coordination, planning, and understanding of friction, leverage, and load distribution. Ancient texts and reliefs depict sledges pulled by hundreds of workers, yet the terrain involved included uneven ground, steep inclines, and long distances. Some blocks were moved uphill, others across rivers, others still lifted to heights that challenge modern cranes. At Baalbek in modern-day Lebanon, 3 stones known as the trilithons sit within the foundation of a Roman temple complex. Each weighs approximately 800 tons. Nearby, in the quarry, lies the stone of the pregnant woman, estimated at over 1,000 tons, partially detached from the bedrock. These stones were not only quarried but transported and precisely placed. The margin for error was negligible. There was no room for repositioning once set. The logic required to calculate weight distribution, ground pressure, and placement accuracy suggests advanced engineering planning rather than brute force improvisation. The Romans themselves, often credited with unparalleled engineering prowess, inherited and expanded upon earlier traditions. Their roads, aqueducts, and bridges spanned continents and survived millennia. Roman concrete, known as opus caementitium, remains one of the most durable building materials ever created. Unlike modern concrete, which degrades within decades, Roman concrete grows stronger over time, thanks to a chemical reaction between volcanic ash and seawater that forms resilient crystalline structures. Modern scientists only recently uncovered the molecular mechanisms behind this process, raising the uncomfortable question of how ancient builders discovered it without modern chemistry. Aqueducts carried millions of liters of water across valleys and mountains using gravity alone, maintaining precise gradients over tens of kilometers. A deviation of even a few centimeters could halt water flow entirely. Yet Roman engineers achieved slopes accurate to within millimeters per meter without laser levels or GPS. They relied on instruments such as the chorobates and groma, tools whose precision continues to impress surveyors today. Still, the scale and consistency of their achievements suggest not isolated brilliance, but a standardized engineering culture. Across the ancient world, similar patterns emerge. In India, entire temples were carved directly from solid rock, top down, with no margin for error. The Kailasa temple at Ellora is one of the most astonishing examples. Carved from a single basalt outcrop, it required the removal of over 200,000 tons of rock. The temple was not hollowed out from the side. It was sculpted downward, starting from the roof and working toward the foundation. A single mistake could have rendered the entire project unusable. Yet the final result displays symmetry, proportion, and structural integrity that rivals constructed buildings. The planning required for such a project defies simple explanations. Builders would have needed complete architectural plans before the first cut was made. They would have had to visualize the final structure in 3 dimensions, accounting for load-bearing columns, internal chambers, and decorative elements, all while carving from the outside inward. This level of foresight aligns more closely with modern architectural modeling than with trial-and-error craftsmanship. In Southeast Asia, the Khmer Empire constructed Angkor, the largest religious monument ever built. Its stone blocks fit with remarkable precision, and its layout reflects complex astronomical alignments. The temple complex mirrors celestial patterns, encoding solstices, equinoxes, and lunar cycles into its geometry. Water management systems beneath the city regulated floods and droughts, sustaining a population of over 1 million people at its peak. These hydraulic networks were so sophisticated that their collapse likely contributed to the fall of the empire, demonstrating both the heights and fragility of ancient engineering systems. Astronomy itself was deeply intertwined with engineering. Many ancient structures aligned with celestial events, suggesting precise observational knowledge accumulated over generations. Stone circles, pyramids, temples, and cities were oriented to solstices, equinoxes, and star risings with astonishing accuracy. This required not only observation but mathematical modeling, timekeeping, and an understanding of Earth's movements. The Great Pyramid of Giza exemplifies this integration of astronomy and engineering. Its base is leveled to within less than 2 centimeters across its entire area. Its sides align almost perfectly with the cardinal directions, deviating by only a fraction of a degree. The pyramid's dimensions encode mathematical constants, including pi and the golden ratio, relationships that modern scholars still debate. Whether intentional or emergent, the precision is undeniable. Inside, narrow shafts align with specific stars, as they appeared thousands of years ago. The pyramid's internal chambers distribute weight in ways that have allowed the structure to survive earthquakes and erosion for over 4,500 years. Modern engineers continue to study its design, using computer simulations to understand how such a massive stone structure maintains stability. What challenges modern logic is not merely that ancient peoples built impressive structures, but that they did so repeatedly across continents, using techniques that appear suddenly and sometimes disappear just as abruptly. In many regions, later cultures failed to replicate the achievements of their predecessors, despite inheriting the same locations and materials. This suggests that knowledge was lost, not steadily accumulated. Engineering knowledge is fragile. It depends on training, tradition, and institutional continuity. When societies collapse due to war, climate change, or political upheaval, technical knowledge can vanish within generations. Skills not written down, not standardized, not transmitted widely are especially vulnerable. The ancient world experienced multiple such collapses, each potentially erasing chapters of engineering history. Yet some techniques endured long enough to leave lasting marks. In China, the construction of the Great Wall involved complex logistics, material science, and regional adaptation. Different sections used different materials depending on local availability, from tamped earth to stone and brick. The wall follows natural terrain, optimizing defensive advantage while minimizing construction effort. Watchtowers were spaced according to signaling requirements, enabling rapid communication across vast distances. In ancient Greece, engineers like Archimedes developed machines that demonstrated deep understanding of mechanics. Cranes, pulleys, and compound lifting systems allowed relatively small teams to manipulate large stone blocks. These devices multiplied force, reduced labor, and increased precision. While simple in principle, their effective deployment requires mathematical understanding and practical experience. Still, even these explanations fall short when confronted with the sheer scale of ancient projects. Labor alone does not explain precision. Time alone does not explain accuracy. Organization alone does not explain innovation. At some point, the logic shifts from incremental development to something more elusive, an engineering worldview fundamentally different from our own. Ancient engineers worked without digital abstraction, without separating theory from practice. Their knowledge was embodied, experiential, and often ritualized. Geometry was not just mathematics. It was sacred order. Astronomy was not just observation. It was cosmic alignment. Engineering was not merely problem-solving. It was a dialogue between humans, materials, and the natural world. This mindset may have enabled solutions that modern logic, constrained by specialization and compartmentalization, struggles to reproduce. Ancient builders observed materials intimately, understanding how stone fractured, how it bent, how water flowed. They designed with redundancy, flexibility, and harmony with natural forces rather than brute resistance against them. As we uncover more evidence through LiDAR scanning, satellite imagery, and advanced archaeology, the ancient world continues to surprise us. Hidden cities emerge beneath jungles. Buried networks of roads and canals reveal vast, organized landscapes. Structures once thought ceremonial reveal functional sophistication. The deeper we look, the harder it becomes to dismiss ancient engineering as primitive. Instead, we are forced to confront a more unsettling possibility, that our modern narrative of linear progress is incomplete, that knowledge can be lost as easily as it is gained, and that beneath the ruins of ancient civilizations lie answers to questions we are only beginning to ask again. This is only the beginning of the story. Across the world, from submerged ruins beneath the oceans to mountaintop fortresses carved into living rock, ancient engineering feats continue to defy modern logic, waiting patiently for us to recognize that the past was far more advanced and far more complex than we ever imagined. Beneath the oceans, ancient engineering tells an even stranger story. Along submerged coastlines, researchers have discovered stone structures that appear intentionally shaped, aligned, and constructed, now lying dozens of meters below sea level. These formations are not random piles of rock. They exhibit straight edges, right angles, terraces, stair-like features, and road-like pathways. Their submersion corresponds to the end of the last ice age, when rising seas swallowed vast tracts of coastal land once inhabited by early civilizations. Off the coast of Japan, the Yonaguni Monument rests beneath the waves, its massive stone steps and platforms cut into solid bedrock. The angles are sharp, the plains flat, the scale monumental. While debate continues over whether it is natural or artificial, many geologists acknowledge that natural erosion alone struggles to account for its symmetry and repeated geometric patterns. If artificial, it would push complex stone engineering far earlier than mainstream timelines currently allow. In the Mediterranean, underwater ruins near Greece, Italy, and Egypt hint at ports, harbors, and cities now lost to rising seas. Ancient engineers clearly understood coastal dynamics, wave forces, and tidal behavior. They built breakwaters, docks, and harbors using interlocking stone blocks that resisted erosion for centuries. The ancient harbor of Caesarea, constructed by Herod the Great, used a revolutionary hydraulic concrete that could set underwater. Modern marine engineers only recently rediscovered similar techniques, once again highlighting a lost chapter of material science. Perhaps most unsettling is the global consistency of certain engineering solutions. Across continents that supposedly had no contact, ancient builders independently developed megalithic architecture, polygonal masonry, astronomical alignments, and massive earthworks. In Central America, the Maya constructed step pyramids aligned with solstices and equinoxes. In Mesopotamia, ziggurats rose in terrace layers, their geometry reflecting cosmic symbolism. In Europe, stone circles and long barrows mark landscapes with mathematical spacing and celestial orientation. These similarities raise uncomfortable questions. Were these solutions independently rediscovered time and again, or do they point to shared principles of engineering knowledge that transcended geography? While direct contact remains debated, the universality of certain methods suggests a deep, intuitive understanding of geometry and physics that emerges when humans work closely with natural forces rather than against them. Earthworks offer another dimension of ancient engineering often overlooked. Long before concrete and steel, ancient societies reshaped entire landscapes using earth, stone, and water. The Nazca lines stretch across the Peruvian desert, massive geoglyphs etched into the ground with astonishing precision. Some lines extend for kilometers in perfectly straight paths, deviating by only a few meters across vast distances. Creating such lines required large-scale planning, surveying techniques, and coordination, all without aerial views. In North America, the builders of Cahokia constructed massive earthen mounds that rival pyramids in volume. Monk's Mound, the largest, required the movement of millions of cubic meters of earth, transported by hand in baskets. Its terraces and orientation reflect astronomical significance, and its stability over centuries reveals sophisticated understanding of soil composition, drainage, and erosion control. Even more astonishing are the ancient road networks carved into rock and earth. In the Andes, the Inca built over 40,000 kilometers of roads across some of the most challenging terrain on Earth. These roads traverse mountains, cross rivers, and span deep valleys using suspension bridges made of woven grass. The roads were engineered with drainage channels, retaining walls, and precisely graded slopes to prevent erosion. Many remain usable today, centuries after their construction. The Inca achieved this without wheeled vehicles, draft animals, or iron tools. Their solutions were not inferior substitutes for missing technologies. They were optimized responses to their environment. Stone staircases follow mountain contours, reducing strain on travelers. Roads were built to endure landslides and earthquakes. Bridges were regularly rebuilt as part of a maintenance tradition embedded in social organization, demonstrating that engineering was as much cultural as technical. Stone carving techniques themselves defy simple explanation. In many ancient sites, tool marks do not match known ancient implements. Some surfaces appear polished to mirror-like smoothness. Others show scoop-like depressions suggesting rotary or oscillating cutting motions. At sites such as Pumapunku, blocks appear to be machined, with grooves, channels, and holes that align with modern industrial tolerances. At Pumapunku, part of the Tiwanaku complex in Bolivia, stone blocks weighing over 100 tons are carved with repeating geometric motifs and interlocking shapes. Some stones contain drilled holes that are perfectly cylindrical, spaced evenly and identical in diameter. The level of standardization implies measuring systems and templates. These were not one-off artistic expressions. They were components of a modular construction system. Modularity itself is an advanced engineering concept. It allows structures to be assembled, disassembled, repaired, and expanded efficiently. Modern prefabrication relies on precise measurements and quality control. The presence of modular stone elements in ancient sites suggests planning processes that extended beyond individual structures to entire architectural systems. Precision measurement is another area where ancient engineering challenges modern assumptions. Many ancient monuments incorporate units of measure that remain consistent across large regions. The Egyptian cubit, for example, was standardized with remarkable accuracy. Cubit rods recovered from different sites differ by only fractions of a millimeter. Maintaining such consistency requires institutional oversight, calibration standards, and training systems. Surveying large areas without modern instruments also required ingenuity. Ancient engineers used sighting rods, water levels, plumb bobs, and geometric relationships to establish straight lines and right angles. Some evidence suggests they used shadows, stars, and solar positions to align structures over long distances. These methods, while simple in principle, demand discipline, patience, and deep understanding to execute flawlessly. One of the most perplexing aspects of ancient engineering is the speed at which some projects appear to have been completed. The Great Pyramid, for example, is often estimated to have been built within a few decades. This implies the placement of millions of stone blocks with extraordinary precision at a rate that challenges modern construction logistics. Even with large labor forces, the organization required to quarry, transport, shape, and place stones continuously suggests an efficiency difficult to reconcile with primitive methods. The absence of clear transitional stages further complicates the narrative. In many regions, the earliest monumental structures already display peak sophistication. There are few examples of crude prototypes leading gradually to perfection. Instead, engineering traditions seem to emerge abruptly, fully realized. This pattern repeats across cultures, from Egypt to the Andes to Southeast Asia. Some researchers propose that much of ancient engineering knowledge was never written down. Instead, it was transmitted orally through guilds, priesthoods, and specialized castes. Techniques were guarded, ritualized, and encoded in symbolism. When these social structures collapsed, the knowledge vanished with them, leaving behind only the finished works and the mystery of their creation. Others suggest that ancient engineering integrated observational sciences we no longer emphasize. Long-term environmental monitoring, seasonal cycles, material aging, and celestial patterns may have informed construction decisions in ways modern short-term thinking often overlooks. Structures were built not just for immediate use, but for endurance across centuries. As modern technology advances, we increasingly rely on machines to compensate for lost skills. Yet ancient engineers compensated for the absence of machines with heightened observation, planning, and collective coordination. Their achievements were not accidents of brute force, but expressions of refined systems thinking. The more we study ancient engineering feats, the more they resist simple categorization as primitive or inferior. Instead, they reveal alternative technological paths that prioritize longevity over speed, harmony over dominance, and knowledge embedded in culture rather than isolated in institutions. And still, this is only another layer peeled back. Beyond stone and earth, beyond roads and temples, ancient engineers manipulated water, sound, light, and even human perception in ways that continue to puzzle researchers today. In the next chapter of this story, we move deeper into those invisible technologies, where ancient logic begins to feel almost alien and modern certainty begins to unravel. Water was one of the most powerful tools in the ancient engineer's arsenal, and nowhere is this more evident than in the hydraulic systems that once sustained entire civilizations. Long before electric pumps or pressurized pipes, ancient societies learned to move, store, filter, and distribute water with extraordinary efficiency. These systems were not crude channels carved into dirt. They were carefully engineered networks designed to function reliably for centuries under changing environmental conditions. In the deserts of Peru, the Nazca constructed underground aqueducts known as puquios. These spiraling stone-lined channels tap into subterranean water sources and guide them gently toward the surface. The spiral access points were not merely entrances. They regulated airflow, pressure, and sediment buildup, ensuring consistent water flow even during droughts. Many puquios remain functional today, a testament to their resilience and the engineers' deep understanding of groundwater behavior. In ancient Persia, engineers developed qanats, underground tunnels that transported water from distant aquifers to arid cities without evaporation losses. Qanats stretched for kilometers beneath the earth, maintaining precise gradients over vast distances. A slope too steep would cause erosion and collapse, too shallow, and the water would stagnate. Thousands of vertical shafts provided ventilation and access during construction, revealing an extraordinary capacity for spatial planning without modern surveying tools. Rome refined water engineering on an imperial scale. Aqueducts delivered clean water to cities, baths, fountains, and households. But beyond transport, Roman engineers mastered water pressure, sedimentation, and flow control. Inverted siphons allowed water to cross valleys by exploiting pressure differentials, a concept rooted in fluid mechanics. Lead and terracotta pipes were manufactured in standardized sizes, implying regulation and quality control across the empire. Sound and vibration also appear to have played roles in ancient construction that modern engineering rarely considers. In certain stone chambers, acoustic properties are so precise that a single voice can produce resonant effects throughout the space. The hypogeum of House Saflini in Malta contained a chamber known as the Oracle Room, where spoken words reverberate at frequencies that induce physical sensations in listeners. The chamber's dimensions and curvature appear intentionally designed to amplify specific sound waves. Some researchers have speculated that ancient builders understood how vibration could affect materials during construction. Even today, ultrasonic vibration is used to cut and shape hard materials. While direct evidence remains elusive, the recurring presence of acoustically optimized spaces across cultures suggests that sound was more than ceremonial. It may have been a functional element integrated into architectural design. Light was another invisible force harnessed with remarkable precision. Many ancient temples were constructed so that sunlight would penetrate inner chambers only on specific days of the year. At Abu Simbel in Egypt, sunlight enters the temple twice annually, illuminating statues deep within the sanctuary. Achieving this required precise calculations of solar angles, seasonal shifts, and architectural orientation. In Mesoamerica, step pyramids were designed to create visual illusions during equinoxes, with shadows forming serpentine shapes that appear to move along staircases. These effects were not decorative accidents. They were engineered experiences, blending astronomy, geometry, and human perception into monumental structures that communicated cosmological knowledge through light and shadow. Heat management further reveals ancient ingenuity. In the Indus Valley city of Mohenjo-daro, buildings were constructed with baked bricks of standardized dimensions, arranged to regulate temperature and humidity. Drainage systems ran beneath streets, carrying waste away efficiently and preventing contamination. Houses were oriented to capture prevailing winds, creating natural ventilation. This level of urban planning rivals modern sustainable design principles. Material science, too, defies expectations. Ancient metallurgists produced alloys whose compositions remain difficult to replicate. Damascus steel, famed for its strength and distinctive patterns, exhibited nanoscale structures only recently identified under electron microscopes. The techniques used to produce it were lost for centuries, surviving only in legend. In South America, ancient builders used organic additives in their mortars, including plant extracts and proteins, to enhance durability and flexibility. Some of these mortars self-heal, sealing microcracks when exposed to moisture. Modern engineers are now studying similar bio-inspired materials, rediscovering principles that ancient cultures applied intuitively. Structural acoustics, optical effects, thermoregulation, and chemical engineering all converge in ancient architecture, suggesting a holistic approach to design. These structures were not assembled from isolated solutions, but conceived as integrated systems. Every element served multiple functions: structural, symbolic, environmental, and experiential. Perhaps most astonishing is how these systems were maintained. Engineering was not a one-time act, but an ongoing relationship between society and infrastructure. Maintenance rituals, seasonal inspections, and communal labor ensured longevity. Knowledge of repair was as important as knowledge of construction, embedded into cultural practices that ensured continuity. When these cultural frameworks collapsed, infrastructure often failed soon after. Without maintenance, even the most brilliant engineering decays. This reinforces the idea that ancient technological decline was not due to inferior design, but to social disruption. The loss of engineering knowledge was not gradual. It was catastrophic. Modern logic tends to isolate technology from culture, treating engineering as purely technical. Ancient logic did not make this distinction. Engineering was inseparable from cosmology, ritual, governance, and daily life. This integration may explain both the heights achieved and the fragility of ancient technological systems. As we push deeper into the ruins of the past, it becomes clear that ancient engineers were not merely solving problems. They were shaping worlds. Worlds where water flowed without pumps, Stone endured without steel, and invisible forces were woven into the fabric of monumental design. And as we turn to the next layer of this story, we confront perhaps the most unsettling question of all. What other engineering principles did the ancients understand that we have not yet rediscovered? Beyond water, sound, and light lies another realm of ancient engineering that unsettles modern assumptions: scale control and systems integration. Ancient builders did not merely construct individual monuments. They engineered entire landscapes, synchronizing cities, roads, agriculture, and ritual spaces into unified systems that functioned for centuries. This level of coordination implies administrative intelligence and technical foresight that modern logic often underestimates. In the Andes, vast agricultural terraces climb mountainsides in precise, repeating patterns. These were not simple retaining walls. Each terrace layer was engineered with stone foundations, gravel drainage, and fertile topsoil arranged to control water flow, prevent erosion, and create microclimates. Different elevations supported different crops, extending growing seasons and reducing risk. Some terraces increased nighttime temperatures by releasing heat absorbed during the day, protecting crops from frost. Modern agronomy has only recently begun to understand these thermal effects. These systems were not isolated to farming. Terraces were linked to road networks, storage facilities, and water channels, forming integrated food production engines capable of sustaining large populations in hostile environments. When these systems were abandoned, erosion followed rapidly, demonstrating how dependent the landscape had become on continuous human engineering. In Mesopotamia, irrigation transformed floodplains into agricultural powerhouses. Canals diverted river water across vast distances, requiring constant maintenance and precise control. Miscalculations could lead to salinization, rendering fields barren. Clay tablets record laws regulating canal upkeep, revealing that engineering management was a matter of state survival. The rise and fall of empires often followed the health of these hydraulic systems. Urban layout itself reflects advanced planning. Many ancient cities follow grid patterns aligned with cardinal directions, prevailing winds and water sources. Streets were sized for airflow and shade. Public spaces were positioned to manage crowds and movement efficiently. Defensive structures were integrated into natural terrain, reducing construction effort while maximizing protection. Some cities exhibit evidence of pre-construction surveying across their entire footprint. This implies that urban plans existed before building began, contradicting the notion of organic, unplanned growth. Such planning required not only vision but reliable methods for transferring designs from abstract concept to physical reality at scale. Energy management, though lacking fossil fuels or electricity, was nonetheless sophisticated. Water wheels powered mills. Wind patterns were harnessed through tower designs that funneled air into living spaces. Gravity was exploited relentlessly, moving water, grain, and materials with minimal effort. Ancient engineers optimized for efficiency because labor and time were precious resources. Even waste was engineered. In the Indus Valley, standardized brick-lined drains ran beneath streets, sloped to carry waste away from homes. Access points allowed for cleaning and maintenance. This was not ad hoc sanitation. It was a city-wide system designed to protect public health. Few medieval cities matched this level of hygiene, highlighting a regression rather than progression in urban engineering. Stone durability itself reflects intentional choice. Ancient builders selected materials not merely for availability, but for long-term performance. Granite resisted erosion. Basalt endured pressure. Limestone weathered predictably. Builders understood how stone aged, choosing materials whose decay would not compromise structural integrity. Some monuments were clearly designed to last thousands of years, not decades. This long-term mindset contrasts sharply with modern construction cycles. Today, buildings are often designed for lifespan efficiency rather than permanence. Ancient logic prioritized endurance, even at the cost of labor intensity. This difference alone explains why ancient feats feel impossible by modern standards. They were built under entirely different assumptions about time. The absence of visible experimentation stages continues to trouble researchers. Trial and error leaves traces. Failed structures, abandoned prototypes, partial collapses. Yet many ancient sites show little evidence of such failures. Either failures were systematically dismantled and recycled, or the builders operated from mature knowledge frameworks developed elsewhere, perhaps over much longer timelines than currently recognized. Some ancient myths and texts describe golden ages when gods or ancestors taught humans the arts of building, measurement, and order. While often dismissed as symbolism, these stories may encode memories of lost knowledge transfers between generations or cultures. When examined through an engineering lens, they reflect reverence for technical mastery rather than supernatural fantasy. The question then shifts from how did they do it to why was it lost? The answer likely lies in the fragility of complex systems. Engineering knowledge requires stable institutions, surplus resources, and long-term continuity. When climate shift, invasions, or internal collapse disrupt these foundations, technical traditions can vanish rapidly. Libraries burn, guilds dissolve, oral knowledge dies with its keepers. Modern society assumes redundancy protects knowledge, yet even today, technological expertise is highly specialized. Remove power grids, supply chains, or digital records, and much modern capability would evaporate within generations. Ancient societies face similar vulnerabilities, amplified by reliance on embodied knowledge rather than written manuals. What remains are the artifacts: stone, earth, water channels, and alignments that silently testify to a different engineering logic. One that did not separate science from meaning, efficiency from beauty, or utility from symbolism. Ancient engineers built with an awareness of cycles, seasonal, celestial, generational, that modern logic often ignores. As we approach the later chapters of this exploration, the uncomfortable realization grows stronger. Ancient engineering feats do not defy logic because they were rational or magical. They defy logic because they were built upon assumptions, priorities, and knowledge systems fundamentally different from our own. And in the ruins they left behind, still standing against time, erosion, and disaster, they pose a final challenge to the modern mind. If such knowledge once existed, shaped the world, and then disappeared, what does that say about the permanence of our own technological achievements? Stone, earth, water, sound, light, and scale all point toward one unavoidable conclusion. Ancient engineering was not fragmented knowledge. It was a unified system. And within that system lies one of the most controversial aspects of all, precision that rivals or exceeds modern industrial tolerances, achieved without industrial machinery. Across multiple ancient sites, measurements repeat with uncanny consistency. Angles recur. Distances scale proportionally. Ratios remain stable across structures separated by kilometers, sometimes continents. This is not coincidence. It is systematized measurement embedded into architecture itself. At the Great Pyramid, the perimeter divided by twice its height yields a value astonishingly close to pi. Whether intentional or emergent, this relationship is precise enough to provoke debate among mathematicians and engineers alike. The pyramid's casing stones were once fitted so tightly that the structure gleamed like a single piece of stone. Their joints were thinner than a human fingernail. Such tolerances require not only skill, but repeatable processes. Repeatability is a hallmark of advanced engineering. It demands standardized tools, calibration methods, and quality control. In ancient Egypt, cubit rods made of granite and wood were used to standardize measurement. These rods were kept under state authority and periodically checked for accuracy. The very existence of such systems undermines the idea of casual or improvised construction. In South America, similar standardization appears without written measurement systems. Stone blocks at Tiwanaku and Cusco follow repeating dimensional patterns. Doorways, niches, and platforms share proportions that suggest a unit of measure consistently applied across generations. This implies training, tradition, and enforcement, not spontaneous craftsmanship. Perhaps even more unsettling are signs of advanced shaping techniques. In some granite blocks, internal corners are perfectly sharp, something difficult even with modern rotating tools. Flat surfaces extend over meters with minimal deviation. Some stones appear to have been softened or shaped in ways that leave tool marks inconsistent with hammering or abrasion. Ancient texts speak cryptically of stones being cut like wood or poured like mud. These phrases are often dismissed as metaphor, yet modern material science has shown that certain chemical and thermal processes can temporarily alter stone properties. While no definitive evidence confirms ancient stone softening technologies, the recurring anomalies keep the question open. Mechanical lifting presents another challenge. Ramps alone struggle to explain vertical placement at extreme heights. Spiral ramps leave little archaeological trace. Internal ramps require advanced planning and precise execution. Counterweight systems, levers, and cranes are plausible, but rarely leave behind evidence proportional to their use. In ancient Greece and Rome, crane technology is well documented. Treadwheel cranes could lift multiple tons using human power efficiently. But the scale of earlier megalithic lifting often exceeds what these devices could handle. This suggests either lost mechanical innovations or methods that minimize lifting altogether through clever staging and terrain manipulation. Some ancient builders appear to grow structures upward rather than assemble them piece by piece. Platforms were raised gradually. Stones slid into place horizontally, and surrounding earth used as temporary scaffolding. Once construction was complete, the earth was removed. This technique leaves minimal trace, erasing evidence of the construction process itself. Time itself may be the most misunderstood factor. Ancient societies measured time differently. Projects were not bound to political terms or quarterly budgets. They unfolded across decades, sometimes generations. Workers were trained from youth to specialize in specific tasks. Knowledge accumulated slowly but deeply, creating expertise modern fast-paced systems rarely allow. This temporal freedom enabled optimization. Engineers could wait for seasons best suited to quarrying or transport. They could align construction stages with celestial events. They could adapt plans over years without abandoning the project. The result was not speed but perfection. The labor force was not merely unskilled manpower. Evidence suggests specialization. Quarry workers, transport teams, masons, surveyors, planners, and overseers. In some cultures, builders held sacred status, their knowledge guarded and revered. This social elevation ensured continuity and respect for technical expertise. Yet even this does not fully resolve the mystery. Some structures incorporate knowledge that appears unnecessary for their function. Astronomical alignments that exceed ritual needs. Precision that offers no obvious structural advantage. Durability far beyond expected lifespan. These choices suggest motives beyond practicality. Ancient engineering may have been an act of legacy, an attempt to communicate across time. Monuments were messages encoded in stone, expressing order, harmony, and cosmic understanding. Their endurance was intentional. They were meant to outlast empires, languages, even memory itself. When modern engineers study these sites, they often focus on how the structures stand. Ancient engineers may have focused equally on what the structures meant. Engineering was not divorced from philosophy. Geometry was sacred. Measurement was moral. Alignment was cosmic. This worldview changes everything. It explains why so much effort was invested where simpler solutions would suffice. It explains why precision exceeded necessity. And it explains why knowledge loss was so devastating, because the knowledge was not merely technical but cultural, spiritual, and institutional. As we near the final chapters of this exploration, the boundary between ancient and modern logic grows thinner. The feats no longer seem impossible. They seem different, built by minds that understood constraints we ignore and ignored constraints we obsess over. The question is no longer whether ancient engineering defies modern logic. It is whether modern logic is sufficient to understand ancient engineering at all. As the evidence accumulates, a deeper pattern emerges, one that modern logic finds difficult to categorize because it does not fit neatly into our definitions of technology. Ancient engineering was not driven by domination over nature, but by synchronization with it. Structures were not imposed upon landscapes. They were grown from them, shaped by terrain, climate, celestial cycles, and material behavior. This approach produced systems that were resilient precisely because they worked with natural forces rather than resisting them. Consider seismic zones. Many of the world's most impressive ancient structures stand in regions prone to earthquakes, yet they survive while modern buildings collapse. In Japan, South America, and the Mediterranean, ancient builders developed techniques that allowed structures to flex, settle, and dissipate energy. Polygonal masonry, trapezoidal doorways, inward-leaning walls, and interlocking stones all contribute to seismic resistance. These solutions were not theoretical. They were empirical, refined through observation across generations. At Machu Picchu, drainage accounts for a majority of the site's construction effort. Beneath the visible stonework lies an invisible network of gravel layers and channels that carry rainwater away, preventing landslides and structural failure. Without this hidden engineering, the city would not exist today. Modern engineers studying the site have noted that its drainage design rivals contemporary standards, yet it was built without formal hydrological models. This emphasis on the unseen appears repeatedly. Foundations were often more elaborate than the structures above them. Subterranean chambers, low distribution layers, and moisture barriers reveal a concern for long-term stability that goes far beyond surface appearance. Ancient engineers invested immense labor in elements no one would ever see, suggesting priorities very different from modern aesthetics-driven construction. Another unsettling aspect is the apparent over-engineering of many ancient sites. Structures were built to withstand forces far beyond those they would realistically encounter. Walls are thicker than necessary, stones larger than required, alignments more precise than function demands. From a modern efficiency standpoint, this seems wasteful. From a longevity standpoint, it is visionary. Modern logic optimizes for cost, speed, and sufficiency. Ancient logic optimized for permanence. When time is measured in centuries rather than fiscal years, engineering decisions change dramatically. Redundancy becomes virtue. Excess becomes insurance. Precision becomes legacy. Knowledge transfer mechanisms further complicate the picture. In the absence of widespread literacy, ancient engineers relied on apprenticeship systems that transmitted embodied knowledge: how stone feels under tools, how it responds to stress, how water behaves after heavy rains. This knowledge was not abstracted into formulas, but internalized through years of practice. Once lost, it was nearly impossible to reconstruct from finished works alone. This helps explain why later civilizations often marveled at, but could not replicate, earlier feats. They inherited the results without the processes. They saw the stones, but not the hands that shaped them. They measured dimensions, but not the lived experience that guided each decision. Ancient collapse narratives reinforced this fragility. When social structures supporting engineering broke down, due to famine, war, climate shifts, or political upheaval, technical knowledge vanished rapidly. Infrastructure failed. Maintenance stopped. Cities declined. The stones remained, but the logic that assembled them was gone. Even today, modern engineering depends on fragile systems, global supply chains, digital records, specialized expertise. Remove these supports, and our own technological knowledge would degrade quickly. Ancient ruins may not represent primitive beginnings, but the remnants of highly optimized systems that could not survive disruption. There is also evidence that ancient engineers intentionally limited dissemination of certain knowledge. Sacred geometries, restricted guilds, and initiation rituals suggest controlled transmission. This may have protected quality, but increased vulnerability. When knowledge is concentrated, its loss is catastrophic. As we approach the end of this inquiry, the notion of lost technology becomes less mystical and more sobering. What was lost may not have been advanced machines, but advanced ways of thinking, systems-level understanding, long-term planning, integration of environment, culture, and engineering into a single worldview. Ancient engineering feats do not require rewriting physics. They require rethinking priorities. They require acknowledging that technological sophistication does not always follow a straight line toward modernity. It can branch, specialize, and disappear. The monuments that remain are not anomalies. They are messages. They tell us that intelligence does not guarantee permanence, that mastery does not ensure survival, and that progress without continuity is fragile. Standing before these structures today, modern logic demands explanations that fit our tools and timelines. But perhaps the real challenge is not explaining how ancient engineers built these wonders. Perhaps the challenge is understanding why we struggle to imagine thinking as they did. Because once we accept that different logics can produce different kinds of mastery, the ancient world no longer feels impossibly advanced. It feels uncomfortably familiar, a mirror showing us what is possible and what can be lost when knowledge is inseparable from culture, time, and meaning. And in that realization lies the final defiance of modern logic. Not that ancient engineers achieved the impossible, but that they achieved the enduring, something our own civilization is still struggling to learn how to do. At the far edge of the story lies a realization that unsettles even the most confident modern engineer. Ancient feats appear less miraculous the more closely they are examined, yet more unsettling the more deeply they are understood. The mystery does not dissolve into simple answers. It sharpens. Because what ancient engineering ultimately reveals is not a missing machine or forgotten tool, but an alternative relationship between knowledge, time, and purpose. Modern logic assumes progress is cumulative, that once a technique is discovered, it is never truly lost. But the ancient record contradicts this assumption again and again. Technologies emerge, reach extraordinary refinement, and then vanish so completely that later cultures struggle even to comprehend them. The Roman recipe for hydraulic concrete disappears for over a millennium. The techniques behind polygonal masonry fade. The precision surveying methods encoded in stone outlast the societies that created them. This pattern forces an uncomfortable conclusion. Knowledge does not survive on intelligence alone. It survives on continuity, on stable transmission, on societies structured to preserve and prioritize long-term understanding over short-term survival. Ancient engineering thrived in worlds where time was measured differently. Projects were conceived beyond individual lifespans. Builders worked knowing they would never see completion. This fundamentally alters design logic. There is no rush, no incentive to cut corners, no tolerance for degradation. Structures become commitments across generations. In such a context, engineering becomes an act of faith, not religious faith, but faith in continuity itself. Faith that knowledge will be preserved, that maintenance will continue, that society will endure. When that faith collapses, engineering collapses with it. The ruins we see today are the frozen endpoints of systems that once functioned flawlessly. They appear mysterious because we encounter them in isolation, stripped of the living knowledge that animated them. We see the bones, not the body, the shell, not the process. Modern attempts to reverse engineer ancient feats often fail because they ask the wrong questions. How heavy was the stone? How many workers were involved? What tools were used? These are mechanical questions. Ancient engineering was systemic. It asked how labor was organized, how knowledge was transmitted, how landscapes were shaped, how materials aged over centuries, how celestial cycles govern planning. Remove any one of these elements, and the system fails. This is why brute force explanations fall short. More workers do not create more precision. More time does not automatically create better alignment. Precision emerges from systems that reward patience, discipline, and repetition. Ancient cultures built such systems, and then lost them. Perhaps the most haunting aspect of ancient engineering is that some structures appear deliberately designed to survive collapse. They endure floods, earthquakes, invasions, and abandonment. They remain functional long after societies that built them vanish. Water channels still flow. Terraces still stabilize mountainsides. Roads still guide travelers. This suggests foresight bordering on pessimism, an awareness that civilizations rise and fall, and that what truly matters is not dominance, but continuity. These structures were built as anchors against oblivion. Modern civilization, for all its technological power, rarely builds this way. Our infrastructure assumes constant maintenance, uninterrupted energy, and stable institutions. Ancient engineering assumed none of these. It planned for absence, for decay, for uncertainty. This difference alone explains why ancient feats feel illogical to us. They were designed under assumptions we no longer share. The final defiance of modern logic, then, is not technical. It is philosophical. Ancient engineers understood something we have forgotten, that the ultimate challenge is not building something impressive, but building something that lasts when everything else fails. And so the stones remain, silent, unmoving, unimpressed by our machines and our theories. They wait, as they always have, for each new generation to ask the same questions, and to realize once again that the greatest technologies are not those that dazzle in the present, but those that endure long enough to challenge the future. This is not the story of a primitive past stumbling toward modern brilliance. It is the story of a different brilliance altogether, one that rose, mastered its world, and then disappeared, leaving behind monuments not to power, but to understanding. And as long as those monuments stand, ancient engineering will continue to defy modern logic. Not because we lack the tools to explain it, but because we may lack the wisdom to fully recognize what was truly built to achieve. When all the stones have been measured, all the theories debated, and all the tools reconstructed, one truth remains stubbornly clear. Ancient engineering does not belong comfortably in the past. It intrudes into the present. It challenges assumptions modern civilization rarely questions about efficiency, progress, and intelligence itself. Modern logic is built on acceleration, faster construction, cheaper materials, shorter lifespans, rapid replacement. Ancient logic was built on restraint. Fewer structures, greater effort, deeper planning, longer endurance. These two logics are not merely different. They are almost oppositional. And that opposition is why ancient engineering continues to feel alien, even unsettling. The ancients did not lack intelligence. They lacked impatience. Many ancient feats appear impossible only because we try to compress them into modern timelines. We imagine monuments built under pressure, under deadlines, under economic urgency. But ancient builders worked under a different psychological horizon. Time was expansive. A project spanning 50 years was not excessive. One spanning a century was not absurd. Knowledge was inherited, not reinvented. Expertise deepened rather than diversified. This allowed refinement instead of disruption. Techniques were perfected slowly, through repetition across generations. Mistakes were corrected not by redesign, but by memory. This is why ancient structures often show a confidence modern construction rarely exhibits. They are not experimental. They are assured. And yet, even with this understanding, certain feats remain deeply uncomfortable for modern explanation. Why do some ancient cuts appear cleaner than modern saw marks? Why do some stones fit better than industrial tolerances require? Why do alignments persist that modern instruments struggle to replicate without digital correction? These questions resist closure because they expose a blind spot in modern thinking. We equate advancement with complexity. We assume that more tools automatically mean more capability. Ancient engineering suggests the opposite is sometimes true, that limitation can sharpen mastery. With fewer tools, ancient engineers observe more carefully. With fewer options, they optimize relentlessly. With fewer chances to rebuild, they plan more thoroughly. Error was costly. Precision was survival. This pressure forged an intimacy with materials that modern engineers rarely experience. Stone was not an abstract property defined by compressive strength tables. It was a living substance with personality, grain, fracture memory, and temperament. Builders knew which stone would split cleanly, which would resist weather, which would sing under stress, which would fail quietly centuries later. This knowledge was not written. It was felt, and because it was felt, it could not survive collapse. When social systems failed, when lineages broke, when apprentices disappeared, the knowledge died silently. No manuals remained. No formula survived. Only the results endured, mute, perfect, and impossible to interrogate directly. This is why ancient engineering so often attracts myth. Gods lifting stones. Giants shaping mountains. Lost civilizations wielding impossible powers. Myth rushes in where logic lacks language. But myth is not proof of ignorance. It is evidence of awe. Even ancient people, closer in time to these feats, sometimes did not understand them. Later Egyptians marveled at earlier pyramids. Romans admired structures they could not replicate. Medieval builders stood beneath Roman ruins and could only guess at their construction. This pattern matters. It means knowledge loss is not theoretical. It is historical. It has happened repeatedly. And it may be happening again. Modern civilization produces staggering technological output, but also produces fragility. Our systems depend on energy abundance, digital memory, global coordination, and uninterrupted specialization. Remove these, and much of modern engineering becomes incomprehensible within a single generation. Ancient engineering assumed disruption. It assumed decay. It assumed silence. That assumption shaped everything. It shaped why stones were oversized, why joints were perfect, why alignments were redundant, why foundations were deeper than necessary. These structures were not built merely to function. They were built to be found. Found by future generations. Found by strangers. Found by civilizations that might not share language, culture, or technology. In this sense, ancient monuments are not infrastructure. They are communication. They speak in geometry because geometry survives translation. They speak in alignment because the sky is shared by all eras. They speak in stone because stone remembers longer than any story. This reframes the question entirely. Ancient engineering does not ask us to marvel at what they could do. It asks us to question what we choose to do. We can build higher, faster, cheaper, but can we build something that still functions without us? Can we build something that makes sense when our records are gone? Can we build something that survives misunderstanding? Ancient engineers answered yes, without electricity, steel, or computers. Not because they were superior, but because they were patient, because they planned for absence, because they respected time as a force greater than power. That is the final defiance of modern logic. Not that the ancients possessed lost machines, not that they broke physical laws, but that they understood something modern civilization resists acknowledging. That intelligence is not proven by speed, that mastery is not proven by scale, and that the highest form of engineering is not innovation, but endurance. The ruins scattered across deserts, jungles, mountains, and seafloors are not relics of ignorance. They are warnings. They remind us that brilliance can vanish, that mastery can be forgotten, and that progress without memory is temporary. Ancient engineering stands not as a mystery demanding explanation, but as a challenge demanding reflection. If civilizations before us could shape stone to last thousands of years, then the question is no longer how they did it. The question is whether we still remember why they did it at all. And once that question is asked, the narrative turns inward, because ancient engineering does not only illuminate the past, it exposes the present. It forces modern civilization to confront an uncomfortable mirror, one in which our technological confidence appears brittle, temporary, and deeply dependent on conditions we barely control. We celebrate innovation, but we rarely ask whether innovation endures. We praise disruption, yet disruption is precisely what erases continuity. Ancient engineers understood continuity as a foundation of all technical achievement. Without it, even the most brilliant solutions dissolve into fragments. What survives from the ancient world survived because it was designed to survive ignorance. Think of what remains functional today. Stone roads that still guide travelers, water systems that still flow, agricultural terraces that still stabilize hillsides. These were not accidents. They were engineered redundancies, systems that did not require constant recalibration, external energy, or centralized control to remain effective. Modern infrastructure, by contrast, is astonishingly capable and astonishingly fragile. Remove electricity and entire cities fall silent. Remove data access and specialized knowledge collapses. Remove supply chains and repair becomes impossible. Ancient engineers assumed such losses as inevitable. This assumption shaped everything. They chose materials that could be repaired locally. They designed systems that degraded gracefully rather than catastrophically. They embedded maintenance into culture rather than outsourcing it to institutions. Engineering was not separate from society. It was society. This integration explains why ancient feats feel so alien to modern logic. We ask how monuments were built, but the more revealing question is how civilizations were organized to support such building for generations without collapse. The answer is not more intelligence. It is coherence. Ancient societies aligned labor, belief, knowledge, and environment towards shared long-term goals. Builders were not marginal workers. They were carriers of sacred responsibility. Their work was meaning, not employment. This transformed effort itself. When labor is identity, precision becomes pride. When construction is ritual, quality becomes non-negotiable. This does not romanticize the past. Ancient societies were harsh, unequal, and often brutal. But they understood something modern systems struggle to replicate. Technical excellence requires social structure. Remove that structure, and tools alone achieve nothing. This is why modern reconstructions so often fail. We attempt to reproduce ancient feats using modern assumptions, short timelines, segmented labor, cost efficiency, and minimal redundancy. We ask machines to replace coherence. They cannot. Even when modern engineers succeed in recreating ancient techniques, they do so artificially, in controlled conditions at enormous expense. The ancients achieved similar results as a matter of routine embedded into daily life. This is not because they possess secret technologies. It is because they possess something far rarer: patience institutionalized at scale. Consider again the question of precision. Precision is not merely a function of tools. It is a function of tolerance for error. Ancient builders could not afford error. A misplaced stone might not be correctable. A flawed alignment might compromise generations. This pressure refines skill far beyond what convenience-driven systems demand. Modern engineering tolerates correction, software updates, structural retrofits, maintenance cycles. Ancient engineering often allowed none of these. Failure meant permanence, and permanence demanded mastery. What unsettles modern logic most is not that ancient feats exist, but that they were normalized. They were not wonders to their builders. They were expectations. The wonders are ours, born of forgetting. As archaeology advances, we continue to uncover evidence of planning that stretches far beyond individual monuments. Entire regions surveyed, landscapes reshaped, resources allocated with foresight that assumes continuity not just of power, but of knowledge. This is why ancient collapse is so revealing. When continuity breaks, the systems unravel rapidly, not because they were poorly designed, but because they were designed for a world that no longer existed. The stones endure, the logic does not. And that may be the most important lesson ancient engineering leaves us. Technology is not independent of culture. Knowledge is not independent of stability, and progress is not independent of memory. The ruins do not mock modern achievement. They warn it. They remind us that every civilization believes itself advanced until it is gone, that every system assumes permanence until it fails, and that intelligence alone does not guarantee survival. Ancient engineering defies modern logic because it was never built to satisfy modern logic. It was built to outlast it. And as long as those structures remain, aligned to skies we still share, rooted in earth we still walk, shaped by hands long turned to dust, they will continue to ask a question no amount of technology can silence. When our own civilization is gone, what will remain to speak for us? And will it still work? And finally, as we stand before the silent witnesses of the ancient world, the lesson crystallizes. Ancient engineering was never about shortcuts. It was never about convenience or spectacle. It was about permanence, mastery, and the integration of knowledge, labor, culture, and environment into systems designed to endure centuries, even millennia. Every stone, every channel, every alignment tells the same story. Intelligence alone is insufficient. Tools alone are insufficient. Only understanding, holistic, patient, and systemic, can create works that survive not just time, but neglect, disaster, and human forgetfulness. The ancients planned for absence. They built for uncertainty. They embedded their wisdom into every material choice, every geometric alignment, every hidden channel and foundation. Their engineering was a message across time, a demonstration that a civilization that respects continuity, understands its environment, and integrates knowledge deeply into its social fabric can achieve feats that seem impossible to future generations. And here's the ultimate challenge. Modern civilization, with all its speed, technology, and power, rarely builds with the same patience or long-term vision. We excel at creation, but we struggle with endurance. We measure success in output, not in survival. The ancient monuments endure not because they were built by gods or aliens, but because they were conceived with foresight that transcended individual lifespans, transcended politics, and embraced the inevitability of change. In the end, ancient engineering does not merely defy modern logic. It teaches it. It reminds us that mastery is not measured by how fast, how high, or how strong, but by how long creation can withstand the test of time, ignorance, and chaos. The stones remain, the channels flow, and the alignments hold their place in the sky. Silent, patient, enduring. They continue to speak across millennia, challenging us not to imitate, but to understand. The true marvel is not that they built such things, but that they built for us to see, to learn, and to be reminded that the highest form of engineering is not innovation alone. It is wisdom, patience, and the courage to build for eternity. If this journey through the genius of ancient engineering has fascinated you, don't just stop here. Dive deeper. Explore the mysteries. Share these insights, and challenge what you thought you knew about human history. Subscribe now. Hit the notification bell, and join us as we uncover more lost knowledge, forgotten civilizations, and engineering feats that continue to defy modern logic. Every like, comment, and share helps bring these incredible stories to more curious minds. Don't just watch history. Be part of rediscovering it.